I'm Juha and I'm a hockey player here at USC. I will be going through some physics concepts and examples with you this semester. And remember, just like on the ice, there's no such thing as luck in physics. Just keep your head up and work hard.
In this problem we have yet another incline. So a car is driving up an incline of 5 degrees at a constant velocity of 20 meters per second. We would like to know how much power is needed from the engine to be able to do this. So power is, as learned, F dot times velocity. So, and let's be clear about this, we need the power from the engine. So this has to be the force from the engine. To evaluate that force, let's draw a free body diagram. So we have the gravity acting down. It has component along the incline like this, and one perpendicular to it. And also we have the angle alpha here. And in that case, this is mg sine alpha, and this one would be mg cosine alpha. Then the force from the engine, Fe, and we also have the drag force, like shown in this figure, dv squared. Let's make it clearer. dv squared. Now in the x direction, so let's define our axes as follows. So that's x and y, so positive directions to the right along the incline. So Newton's second law, or first law, says that the net force must be 0 because this is moving at constant speed and constant velocity. So we have force from the engine, and then the component of gravity that we are fighting against, and also the drag force that is slowing us down, like this. And these have to be 0, like I just explained. So Fe, force from the engine, mg sine alpha plus dv squared. And now back to the power. So P from the engine is dot product of Fe and velocity, and because they are both in the same direction along the incline, the dot product is just the product of their magnitudes. So we have mg sine alpha plus dv squared times v, and put in the numbers: 1000 kg, 9.81 meters per second squared of sine 5 degrees, plus the drag coefficient 0.5 kg per meter, typical for an automobile in production, and velocity 20 meters per second squared, and velocity once more. This gives about 21,000 watts, so 21.1 kilowatts. And horsepower might be more familiar unit, so 1 horsepower is in fact 0.746 kilowatts, so 1 kilowatt is 1 over 0.746 horsepower, which is about 1.34 horsepower. So if we multiply this one, we get about 34 horsepower. which is easily doable from a typical car engine these days.